Tonight, we're going to explore something that most people assume they already understand. Empty space, the vacuum, the void, the nothing between things. The region where there is no air, no matter, no light, no sound, no substance of any kind. Most people have a clear mental image of what empty space is. It is what astronauts float through. It is what separates the planets. It is the background against which the stars shine. It is, by definition, the absence of everything. And it is one of the most dangerous, most active, most consequential, most genuinely strange regions in the entire universe. Not in the way that most space documentaries mean when they call space dangerous. Yes, space will kill an unprotected human being in under 2 minutes through a combination of pressure loss, hypoxia, and temperature extreme. That is not what we are talking about tonight. That is the danger of the absence of Earth's atmosphere. We are talking about something deeper and stranger than that. The danger of the vacuum itself, of the nothing, because the nothing is not nothing. Empty space is filled with energy, not hypothetically, not theoretically in the way that physicists sometimes wave their hands and say, well, in principle, there might be energy there. Measurably, confirmably, experimentally verified energy. Energy that creates forces between objects with no mechanism connecting them. Energy that makes objects accelerate for no apparent reason. Energy that stretches the fabric of space-time apart faster than light can traverse it. Energy whose predicted value is off from its measured value by the largest discrepancy in the history of physics, a factor of 10 to the power of 120. Empty space is filled with particles, pairs of particles that appear from nothing and vanish into nothing on timescales so short that they technically cannot be observed, except that they can be observed because they leave marks. They change the energy levels of atoms in ways that can be measured to 12 decimal places. They create forces between metal plates that have been precisely measured in laboratory. They may determine the ultimate fate of black holes. Empty space is filled with fields, not just the fields we know about. The electromagnetic field and the gravitational field and the quantum fields of the standard model of particle physics. Possibly fields we do not yet understand, fields whose properties we can measure and whose effects we can observe, but whose fundamental nature remains one of the deepest unsolved problems in all of science. And empty space may be unstable, not the space in your living room, not the space between here and the nearest star, but the vacuum of the universe itself, the particular configuration of quantum fields that we call empty space may be sitting at a local minimum of energy rather than the global minimum. If that is true, and the calculations suggest it may well be, then somewhere in the universe at some point in time, a bubble of true vacuum is going to nucleate, and that bubble is going to expand in every direction at the speed of light, and everything it touches will be converted from the physics we know into physics we cannot survive and cannot predict. 7 things that make empty space genuinely, physically dangerous. Not metaphorically dangerous, not cinematically dangerous. Dangerous in ways that the equations of physics, the most precisely tested theories ever constructed, tell us with varying degrees of certainty are real. Before we begin, if the idea that the empty space around you right now is more complicated and more consequential than you imagined is the kind of thing that keeps you thinking, hit like or subscribe. It helps us reach more people who want to understand things like this. Now, let's begin. 2 Dutch physicists, Hendrik Casimir and Dirk Polder, are working at the Philips Research Laboratories in the Netherlands when Casimir has an insight that will eventually force physicists to completely rethink what empty space is. Working from calculations by Niels Bohr on the forces between large molecules, Casimir derives a prediction that seems, at first glance, impossible. Take 2 flat, uncharged metal plates, Place them in a perfect vacuum. Bring them very close together, but not touching. Remove every possible influence except their geometry. According to Casimir's calculation, the plates will attract each other, not because of any charge, not because of any magnetic field, not because of any known force, simply because they exist in a vacuum and are close to each other. This is the Casimir effect, and its explanation requires accepting something profound about the nature of empty space. In classical physics, the vacuum between the plates is empty. Nothing. Zero energy, zero fields, zero activity. The plates would feel no force from the vacuum because the vacuum has nothing in it to push or pull. But quantum mechanics says the vacuum is not empty. The uncertainty principle, one of the foundations of quantum mechanics, says that no physical quantity can be simultaneously at a precisely defined value and also not changing. Energy cannot be exactly zero everywhere and also exactly stable. The vacuum is subject to quantum fluctuations. It seethes with pairs of virtual particles. Particle and antiparticle pairs that appear from nothing, exist for an almost unimaginably brief moment, and annihilate back into nothing. This fluctuating vacuum has energy, not a little energy. According to naive calculations from quantum field theory, it has an enormous amount of energy, the zero-point energy of all the quantum fields. And this vacuum energy has a measurable effect on the Casimir plates. The two metal plates, by confining the space between them, restrict which wavelengths of virtual photons can exist in that space. Long wavelength virtual photons cannot fit between closely spaced plates. Outside the plates, all wavelengths are permitted. This difference in the spectrum of virtual particles between the interior and exterior of the plate gap produces a pressure imbalance. The outside pushes harder than the inside. The plates are pushed together by the quantum vacuum itself. Casimir predicted this in 1948. It was first measured experimentally by Marcus Sparney in 1958, confirming the effect existed though with limited precision. In 1997, Steve Lamouros at the University of Washington measured the Casimir force with a precision of 5%, precisely confirming Casimir's quantum mechanical prediction. Empty space pushes things together with a measurable, calculable, precisely confirmed force. The nothing between two plates is doing something. This is the beginning of understanding why empty space is dangerous. Not because of what is absent, because of what is present in the absence. Shocking discovery. Number 1. The quantum vacuum is boiling with energy, and it manipulates atoms. The Casimir effect is dramatic, but its most important implication is not the force between plates. It is what the force tells us about the nature of empty space and how that nature affects everything in the universe. Every atom in the universe is sitting in the quantum vacuum, surrounded by it, permeated by it. The electron orbitals of every atom in your body are being constantly buffeted by quantum vacuum fluctuations. The hydrogen atom in a water molecule is not sitting in peaceful empty space between its electron and its proton. It is sitting in a seething, fluctuating, energetic quantum medium that is constantly interacting with its quantum fields. This interaction has measurable consequences. One of the most precisely measured phenomena in all of physics is the Lamb shift, discovered in 1947 by Willis Lamb and Robert Rutherford. When they measured the energy levels of the hydrogen atom with extraordinary precision, they found that two specific energy levels that quantum mechanics without vacuum fluctuations predicted should be exactly equal were in fact slightly different. The difference, the Lamb shift, is tiny, but it is real and it is measurable. The cause is the quantum vacuum. Virtual photons from the vacuum interact with the electron in the hydrogen atom, causing it to jiggle slightly, which slightly modifies its average position relative to the proton, which slightly changes the energy level. The Lamb shift is the vacuum reaching into atoms and changing their properties. This is not a special property of hydrogen. Every atom is affected by vacuum fluctuations. The chemical properties of every element, the precise wavelengths of light that every substance emits and absorbs, the exact energies of every molecular bond, are all slightly modified from what they would be in a truly empty classical vacuum. The periodic table of elements, the foundational document of chemistry, would be slightly different in a universe with no quantum vacuum. More practically, spontaneous emission, the phenomenon by which excited atoms lose energy by emitting photons without any external cause, is a vacuum effect. In classical physics, an excited atom would remain in its excited state indefinitely unless some external electromagnetic field stimulated it to emit. But atoms do not remain in excited states indefinitely. They emit photons spontaneously, converting their excess energy to radiation on timescales of nanoseconds to microseconds. The vacuum causes this. The virtual photons of the quantum vacuum are constantly interacting with excited atoms, stimulating them to emit real photons. Spontaneous emission is vacuum-stimulated emission. The vacuum is constantly poking every excited atom in the universe, triggering the emission of photons that would not otherwise occur. This matters enormously. The light from every star comes ultimately from spontaneous emission by excited atoms in the stellar atmosphere, triggered by vacuum fluctuations. The fluorescence of every luminescent material is spontaneous emission triggered by the vacuum. Every atomic clock, every laser, every piece of quantum optical technology depends on spontaneous emission. The quantum vacuum is not just doing something, it is doing something that is essential to almost every optical and atomic process in the universe. The vacuum is not empty, it is an active participant in physics. And its participation is not gentle or passive. It changes the structure of atoms. It causes light emission. It creates forces between objects. The nothing is doing work. Shocking discovery. Number 1. The quantum vacuum is boiling with energy, and it manipulates atoms. The Casimir effect is dramatic, but its most important implication is not the force between plates. It is what the force tells us about the nature of empty space and how that nature affects everything in the universe. Every atom in the universe is sitting in the quantum vacuum, surrounded by it, permeated by it. The electron orbitals of every atom in your body are being constantly buffeted by quantum vacuum fluctuations. The hydrogen atom in a water molecule is not sitting in peaceful empty space between its electron and its proton. It is sitting in a seething, fluctuating, energetic quantum medium that is constantly interacting with its quantum fields. This interaction has measurable consequences. One of the most precisely measured phenomena in all of physics is the Lamb shift, discovered in 1947 by Willis Lamb and Robert Rutherford. When they measured the energy levels of the hydrogen atom with extraordinary precision, they found that two specific energy levels that quantum mechanics without vacuum fluctuations predicted should be exactly equal were in fact slightly different. The difference, the Lamb shift, is tiny, but it is real and it is measurable. The cause is the quantum vacuum. Virtual photons from the vacuum interact with the electron in the hydrogen atom, causing it to jiggle slightly, which slightly modifies its average position relative to the proton, which slightly changes the energy levels. The Lamb shift is the vacuum reaching into atoms and changing their properties. This is not a special property of hydrogen. Every atom is affected by vacuum fluctuations. The chemical properties of every element, the precise wavelengths of light that every substance emits and absorbs, the exact energies of every molecular bond, are all slightly modified from what they would be in a truly empty classical vacuum. The periodic table of elements, the foundational document of chemistry, would be slightly different in a universe with no quantum vacuum. More practically, spontaneous emission, the phenomenon by which excited atoms lose energy by emitting photons without any external cause, is a vacuum effect. In classical physics, an excited atom would remain in its excited state indefinitely unless some external electromagnetic field stimulated it to emit. But atoms do not remain in excited states indefinitely. They emit photons spontaneously, converting their excess energy to radiation on timescales of nanoseconds to microseconds. The vacuum causes this. The virtual photons of the quantum vacuum are constantly interacting with excited atoms, stimulating them to emit real photons. Spontaneous emission is vacuum-stimulated emission. The vacuum is constantly poking every excited atom in the universe, triggering the emission of photons that would not otherwise occur. This matters enormously. The light from every star comes ultimately from spontaneous emission by excited atoms in the stellar atmosphere, triggered by vacuum fluctuations. The fluorescence of every luminescent material is spontaneous emission triggered by the vacuum. Every atomic clock, every laser, every piece of quantum optical technology depends on spontaneous emission. The quantum vacuum is not just doing something, it is doing something that is essential to almost every optical and atomic process in the universe. The vacuum is not empty, it is an active participant in physics. And its participation is not gentle or passive. It changes the structure of atoms. It causes light emission. It creates forces between objects. The nothing is doing work. Shocking discovery. Number 2, the vacuum has energy, and that energy is tearing the universe apart. The vacuum energy measured in the Casimir effect and the Lamb shift is real. It is confirmed. The question is how much of it there is. In quantum field theory, calculating the zero-point energy of the vacuum requires adding up the ground state energy of every quantum field at every point in space, up to some maximum energy scale. Different quantum fields contribute different amounts. Summing them up with the assumption that quantum field theory is valid up to the Planck scale gives a vacuum energy density of approximately 10 to the 97th kilograms per cubic meter. The measured energy density of what we call the cosmological constant, the dark energy that is causing the accelerating expansion of the universe, is approximately 10 to the negative 27th kilograms per cubic meter. The ratio of the predicted to the observed value is 10 to the 120. The theoretical prediction is 120 orders of magnitude larger than what is observed. This is the largest discrepancy between theoretical prediction and experimental measurement in the history of physics. It is not a small error. It is not a matter of off by a factor of 2 or even 1,000. It is 1 followed by 120 zeros. Something is cancelling almost all of the vacuum energy. Some mechanism is reducing the predicted value to the observed value with a precision of 1 part in 10 to the 120. And we have no idea what that mechanism is. This is the cosmological constant problem, and it is widely regarded as the deepest unsolved problem in fundamental physics. It sits at the intersection of the two most successful theories ever developed, quantum mechanics and general relativity, and reveals that something is profoundly wrong with how we think about the vacuum. But here is the danger. What we do observe, the tiny residual vacuum energy that survived whatever cancellation mechanism operates, is enough to be tearing the universe apart. The observed dark energy, 120 orders of magnitude smaller than the theoretical prediction, is still sufficient to drive the accelerating expansion that will eventually remove every galaxy outside our local group from our observable universe. The vacuum energy that remains after almost total cancellation is the most consequential phenomenon in the universe's long-term future. It is determining the ultimate fate of everything. And the vacuum energy that was cancelled, whatever mechanism produced that cancellation, is the most important unknown in all of physics. The vacuum is dangerous not just because it contains energy, but because the amount of energy it contains and why it contains that specific amount rather than some other amount is a mystery whose resolution could change everything about how we understand the universe. The nothing is doing something, and the something it is doing is driving the largest scale dynamics of the cosmos, while the reason for the specific amount it is doing it with remains completely opaque to our best theories. Shocking discovery. Number 3. The vacuum gives particles their mass. Here is something that most people who have heard of the Higgs boson do not fully understand. The Higgs boson is not what gives particles their mass. The Higgs field gives particles their mass. The Higgs boson is just the ripple that appears when you excite the Higgs field. And the Higgs field is a property of the vacuum. In the standard model of particle physics, the vacuum is not empty, even setting aside the virtual particle fluctuations we have already discussed. The vacuum has a specific value of the Higgs field. This value is not zero. It is a specific non-zero number, approximately 246 billion electron volts, that characterizes the Higgs field everywhere in the universe at all times. This non-zero value of the Higgs field in the vacuum is called the Higgs vacuum expectation value, and it is responsible for the masses of almost everything. Without the Higgs field's non-zero vacuum expectation value, electrons would be massless. They would travel at the speed of light. They would not form stable orbits around nuclei. Atoms would not exist. Without atoms, there would be no chemistry, no planets, no biology, no US. The W and Z bosons, the carriers of the weak nuclear force responsible for radioactive decay and nuclear reactions in stars, would also be massless. The weak force would become long-range like electromagnetism, completely changing nuclear physics. Stars could not burn in the way they do. The specific value of the Higgs field in the vacuum is what makes the universe the way it is. It is what makes atoms stable enough to form molecules. It is what makes the weak force weak enough to allow stars to burn for billions of years rather than exploding instantly. It is what makes the universe hospitable to complexity. And this value, the 246 billion electron volt vacuum expectation value of the Higgs field, is not derived from any deeper principle. It is measured. We know what it is. We do not know why it is that value rather than any other value. It is a property of the vacuum, a choice the universe made when it settled into its current configuration, and we cannot yet explain why it made that choice. Here is where the danger becomes acute. The Higgs field in the vacuum could, in principle, have a different value. The vacuum expectation value we have is a minimum of the Higgs field's potential energy, a valley in the landscape of possible field configurations. But calculations suggest that this valley may not be the lowest possible valley. There may be a deeper minimum, a lower energy configuration at some different value of the Higgs field. If the universe's vacuum is currently sitting in a local minimum rather than the global minimum of the Higgs potential, then the vacuum is technically metastable. It is stable against small perturbations, the way a ball sitting in a shallow valley is stable against small bumps. But given enough time or a large enough fluctuation, it could tunnel through the barrier and fall into the lower energy state. This is vacuum decay. This is the vacuum's most dangerous property. Shocking discovery. Number 4. The vacuum might be unstable and the universe might already be ending. In 2012, physicists at CERN measured the mass of the Higgs boson to be approximately 125 billion electron volts. This measurement was one of the most important results in the history of particle physics. It completed the Standard Model, confirming the existence of the last undetected particle. It also suggested, when plugged into calculations of the Higgs field potential, that the vacuum of our universe is metastable. The calculation is this: the stability of the Higgs vacuum depends on the Higgs boson mass, the top quark mass, and the strong coupling constant, 3 quantities that can be measured experimentally. When those measured values are used to calculate the stability of the Higgs potential, the result is that the current vacuum sits not in a globally stable configuration, but in a metastable one, a local minimum, a false vacuum. The word false is key. A false vacuum looks stable. It feels stable. There is no sign from within a false vacuum that anything is wrong. The atoms and molecules and physical processes happening within a false vacuum all behave consistently with the laws of physics as they apply in that vacuum. Everything seems fine until a bubble of true vacuum nucleates somewhere. Vacuum decay begins when a quantum fluctuation produces a small region, a bubble, in which the Higgs field has tunneled to the lower energy true vacuum state. This bubble has lower energy than the surrounding false vacuum. It is energetically favorable to expand, and expand it does at the speed of light in all directions simultaneously. Inside the bubble, the physical constants are different. The Higgs vacuum expectation value is different. This means the masses of elementary particles are different. The weak force has different properties. Nuclear physics is different. Atoms, if they can form at all in the new vacuum, are different. Chemistry is different. Everything the expanding bubble encounters is instantly and completely transformed from the physics we know into a different physics. Stars are converted. Planets are converted. Living beings are converted. Not in any process that takes time for the beings to experience. The bubble wall travels at the speed of light. There is no warning. There is no signal that can outrun the bubble. The first indication any observer in the false vacuum would have that the bubble had arrived is the conversion of their own atoms into something else, which is simultaneous with the cessation of any further observation. How likely is this? The calculation depends sensitively on the exact values of the particle physics parameters, particularly the top quark mass, which is known less precisely than the Higgs mass. Current calculations suggest the vacuum is metastable rather than stable, but the uncertainty in the top quark mass means the calculation could be off in either direction. The timescale for vacuum decay, if it occurs, is estimated at something like 10 to the hundreds of years, far longer than the current age of the universe. The probability of vacuum decay occurring anywhere in our observable universe in the next billion years is extraordinarily small. But here is the haunting part. The bubble, if it has nucleated somewhere in the universe, travels at the speed of light. We would receive no advance warning. We cannot detect it coming. The universe could be in the process of vacuum decay right now, with a bubble expanding at light speed toward us from some distant region, and we would not know until the moment it arrived. The vacuum may already be betraying us. The nothing may already be becoming something lethal. And because nothing travels faster than light, we cannot know. This is the vacuum's deepest danger. Not the forces it creates, or the energy it contains, or the particles it produces. The possibility that the specific configuration of quantum fields that constitutes our physics, the configuration that makes atoms and stars and life possible, is sitting at a local minimum, waiting for a fluctuation that has perhaps already occurred somewhere in the observable universe. We live in a vacuum that might be lying to us about its own stability. Let's step back from the extremes for a moment and talk about something that affects us right now, in this era, in ways that are already observable. The Voyager spacecraft, whose journeys we have traced through multiple previous videos, carried instruments designed to measure properties of the interstellar medium. The space between stars, beyond the heliosphere where the sun's solar wind gives way to the broader interstellar environment. That interstellar space is not empty in any conventional sense. It contains approximately 1 hydrogen atom per cubic centimeter. It contains magnetic fields. It contains cosmic rays, high-energy particles from violent events across the galaxy. It contains dust grains. But between those atoms, in the space between the space, in the regions where no atom is present, there is still the quantum vacuum, still the Casimir energy, still the virtual particle pairs, still the Higgs field at its vacuum expectation value, still dark energy, the residual vacuum energy that is driving the accelerating expansion. The quantum vacuum is not a property of regions near matter. It is not generated by atoms or fields or particles. It is the ground state of the universe itself, present everywhere, even in regions no atom has ever occupied. The most remote corner of intergalactic space, the most perfect vacuum achievable. The region between galaxy clusters in the vast cosmic voids is permeated by the quantum vacuum with all its properties. Every cubic centimeter of space in the observable universe, from the heart of the densest neutron star to the most isolated region of the cosmic void, is filled with the quantum vacuum. The vacuum is not a place without things. It is a thing that is everywhere. Shocking discovery. Number 5. The vacuum remembers. Nothing, which means black holes, face an existential crisis. The Hawking radiation that black holes emit, which we have discussed in previous videos, is a vacuum phenomenon. It is produced at the event horizon, the boundary of the black hole, by the interaction of the quantum vacuum with the extreme space-time curvature of the black hole. Near the event horizon, virtual particle pairs from the vacuum are torn apart by the tidal gravitational forces. Normally, virtual particles appear from the vacuum and annihilate back into it in a time so short that they cannot be detected directly. But near a black hole's event horizon, one particle of a virtual pair can fall inside the horizon while the other escapes to infinity. The escaping particle becomes real, carrying real energy away from the black hole. The infalling particle effectively carries negative energy into the black hole, reducing its mass. This is Hawking radiation, and it comes entirely from the quantum vacuum being distorted by the geometry of the black hole. But Hawking radiation creates a profound problem. As a black hole emits Hawking radiation and loses mass, it eventually evaporates completely. All the information about the matter that originally formed the black hole, or fell into it subsequently, appears to be lost. The Hawking radiation, being thermal, carries no information about what the black hole originally contained. A black hole formed from a stellar collapse, and a black hole formed from an equal mass of antimatter, and a black hole formed from an equal mass of old novels all produce identical Hawking radiation. If the black hole evaporates and the Hawking radiation is truly thermal and information-free, then the information about what the black hole contained has been permanently destroyed. Not scrambled, not hidden, not encoded somewhere inaccessible. Destroyed. Gone. The quantum state of the infalling matter has ceased to exist as a distinct quantum state. This violates quantum mechanics. Quantum mechanical evolution is unitary, meaning information is conserved. The total information content of a closed quantum system never changes, only its form. Black hole evaporation, taken at face value with thermal Hawking radiation, produces a non-unitary evolution that destroys information. This is the black hole information paradox, and it has been one of the central problems in theoretical physics for 50 years. The paradox arises specifically because the Hawking radiation is a vacuum process. The vacuum near the event horizon does not know what fell into the black hole. It produces thermal radiation determined only by the black hole's temperature, which is determined only by the black hole's mass. The vacuum's ignorance is the source of the paradox. Various resolutions have been proposed. The most popular current idea involves what are called firewalls or fuzzballs, or holographic encoding of information on the event horizon. In each case, the resolution requires modifying what we thought we understood about either quantum mechanics, general relativity, or the properties of the vacuum at the event horizon. Recent work, including calculations involving the so-called island formula in the context of quantum gravity, suggests that information is preserved in the Hawking radiation through subtle quantum gravitational effects that become important at late times in the evaporation process. But the mechanism is not yet fully understood, and the specific way in which the quantum vacuum encodes and preserves the information remains one of the deepest unsolved problems connecting vacuum physics to the fate of information in the universe. The vacuum's interaction with black holes is dangerous not just for any information that falls in. It is dangerous for our entire framework of understanding quantum mechanics and general relativity. The vacuum at the event horizon is where the two most successful theories in physics come into direct conflict, and the danger is not physical in the immediate sense, but intellectual in the deepest sense. The vacuum is showing us that our best understanding of reality is incomplete. Shocking discovery. Number 6. The expanding vacuum is creating particles from nothing right now. There is a phenomenon called the Unruh effect, predicted by William Unruh in 1976, that reveals something extraordinary about the relationship between the quantum vacuum, acceleration, and the nature of particles themselves. An observer at rest in empty space sees the quantum vacuum in its ground state. No particles, just the seething, fluctuating vacuum. But an observer who is accelerating through that same empty space sees something different. The accelerating observer sees thermal radiation, a bath of real particles with a temperature proportional to the acceleration. The same region of space, the same physical vacuum, appears as empty from one observer's perspective and as filled with thermal radiation from another observer's perspective, simply because of their different states of motion. This is profoundly disorienting. It means that particles are not absolute. What counts as a particle depends on who is asking. An observer in uniform motion and an accelerating observer disagree about whether the vacuum contains particles. The accelerating observer does not see more particles because there is actually something there that the inertial observer misses. They see particles because accelerated motion changes the relationship between the observer and the quantum vacuum in a way that manifests as particle creation. The Unruh effect has never been directly measured because the temperatures involved for laboratory achievable accelerations are extraordinarily small, far below what any current detector can distinguish from background noise. But the effect is theoretically well established and is mathematically closely related to Hawking radiation, which has been extensively studied and is more widely accepted. The Unruh effect reveals something about the nature of the vacuum that is deeply counterintuitive. There is no observer, independent answer to the question of how many particles are in a given region of space. The answer depends on the observer's state of motion. The vacuum that appears empty to one observer appears full to another. This has practical implications for cosmology. The universe itself is expanding, and the expansion has a horizon, the cosmic event horizon, beyond which events cannot communicate with us. This horizon is similar in important respects to the event horizon of a black hole. And just as black holes produce Hawking radiation from their event horizons, the cosmic event horizon produces a form of radiation called de Sitter radiation, or Gibbons-Hawking radiation. This radiation is extraordinarily faint, with a temperature of about 10 to the minus 30. Kelvin, far below any measurable threshold. But it is physically real. The expanding universe, with its accelerating expansion driven by dark energy, is creating particles from the vacuum through the same mechanism by which black holes create Hawking radiation. The universe is manufacturing particles from empty space right now, not at a rate that has any significant macroscopic effect in the current era, but over cosmic timescales, as the universe continues to expand and the de Sitter temperature represents the ultimate minimum temperature the universe approaches. This vacuum particle production is the last remaining physical process. In the far future, after all stars have died and all matter has decayed, the de Sitter radiation of the expanding vacuum will be the only physical process still operating. The vacuum creates. It does not just sit there passively. It responds to geometry, to acceleration, to expansion by producing particles from nothing. This particle production is the vacuum's most active behavior. And in the long run, it may be the universe's last word. Shocking discovery number 7. The vacuum has already changed once, and the evidence is all around us. The universe did not always have the vacuum we have now. In the very early universe, at energies above a few 100 billion electron volts, the Higgs field was at 0. The vacuum expectation value of the Higgs field was 0. This means all particles were massless. The electroweak symmetry, the unified theory that describes electromagnetism and the weak nuclear force as a single force, was unbroken. The W and Z bosons were massless, like photons, and electromagnetic and weak forces were indistinguishable at high energies. As the universe cooled, falling below the electroweak phase transition temperature of approximately 2 × 10⁻⁻⁵ degrees Kelvin, something happened to the vacuum. The Higgs field underwent a phase transition. It settled from 0 into its current vacuum expectation value of 246 billion electron volts. The electroweak symmetry broke. The W and Z bosons acquired masses. The electromagnetic and weak forces separated into distinct forces with different ranges and strengths. The vacuum changed. The properties of empty space transformed from one configuration to another. Everything in the universe at that moment, every particle, every field, every interaction, was affected by this change in the vacuum. The masses of the elementary particles came into existence at that moment. The distinct forces that govern atomic physics crystallized from what had been a single unified force. This phase transition is called electroweak symmetry breaking, and it occurred when the universe was approximately 10⁻⁻12 seconds old, a trillionth of a second after the Big Bang. The universe had been in existence for less time than it takes light to cross a proton, and the vacuum had already undergone a fundamental transformation that would determine the structure of all subsequent physics. The evidence for this transition is all around us. The fact that the W and Z bosons are heavy and the photon is massless is direct evidence. The fact that the electromagnetic and weak forces have different ranges and strengths is direct evidence. The very existence of the Higgs boson, confirmed in 2012, is the ripple left by the Higgs field's occupation of its current vacuum state. Every property of every atom, in every molecule, in every object in the universe, reflects the outcome of that vacuum phase transition. But there was likely an earlier transition too. At energies above the electroweak scale, there may have been a grand unification transition at which the electroweak and strong forces were also unified. At energies higher still, gravity may have been unified with the other forces. Each of these transitions involved the vacuum moving from one configuration to another. Each changed the effective laws of physics, and there may have been an even earlier and more dramatic transition. Inflation, the extraordinarily rapid exponential expansion of the early universe, is thought to have been driven by the energy of the vacuum in a particular high-energy configuration. The inflaton field, whatever it is, was sitting at a high-energy false vacuum state. When it rolled down to a lower energy state at the end of inflation, the energy released reheated the universe to the hot, dense plasma of the early Big Bang. The end of inflation was a vacuum phase transition. The universe we live in is the product of multiple vacuum phase transitions. Each one changed the nature of empty space. Each one restructured the effective laws of physics governing everything that exists. We are living in a vacuum that has already changed several times from the vacuum that existed at the Big Bang. The question is whether it will change again. The metastability of the Higgs vacuum, if confirmed by future measurements of the top quark mass and other parameters, suggests that the vacuum may change again in the future. The universe may be sitting in a false vacuum, waiting for the quantum fluctuation that will trigger the next phase transition, the next fundamental restructuring of what empty space is and what the laws of physics are. The vacuum changed to give us the world we have. It may change again to take it away. Let us trace the specific danger from closest to farthest in time. Right now, the immediate danger of the quantum vacuum to human beings is zero in the practical sense. The virtual particle fluctuations that permeate the vacuum are at energies and timescales so small that they have no macroscopic biological effect beyond the ones they have always had. The Casimir effect operates on scales of micrometers and produces forces of micronewtons. The Lamb shift is relevant to atomic physics, but not to human health. Spontaneous emission triggers by the vacuum is what makes atoms emit light, which is helpful rather than dangerous at the biological level. The dark energy problem is a danger on cosmic timescales. The accelerating expansion driven by vacuum energy will eventually, in billions to hundreds of billions of years, remove every galaxy cluster outside our local group from our observable universe. This is a profound long-term existential limitation on the reach of any civilization based in our corner of the cosmos. But it is not an immediate danger. The nearest galaxy outside the local group, the Andromeda Galaxy's satellite, is not going to cross the cosmic horizon for billions of years. The vacuum stability question is both the most remote in time and the most immediately terrifying to think about. If vacuum decay can occur, the timescale is estimated at greater than 10 to the hundreds of years, far longer than the age of the universe. The probability of vacuum decay in any given century is extraordinarily small, but it is not zero. And the nature of the danger, the impossibility of detection before arrival, the complete conversion of physics at the bubble wall, makes it categorically different from other existential risks. The only comfort in this regard is that we are here to discuss it. If the vacuum were significantly more unstable than current calculations suggest, vacuum decay might have occurred already somewhere in the observable universe's history, producing a bubble that should by now have swept through our location. The fact that we are here is evidence, though not proof, that the vacuum is at least moderately stable. Anthropic reasoning applied to vacuum stability says that we should not be surprised to find ourselves in a universe where the vacuum is stable enough to permit our existence. But this does not tell us how stable it is beyond the minimum required for our existence. The vacuum could be marginally stable or overwhelmingly stable, and the anthropic argument gives us limited ability to discriminate. What Hawking radiation and the Unruh's effect tell us is that the danger from the vacuum is not purely future tense. The vacuum is doing things right now. It is producing particles from nothing in quantities too small to measure directly, but large enough to have changed our understanding of physics fundamentally. It is interacting with every atom in the universe, modifying their properties in ways we can measure to 12 decimal places. It is driving the expansion of the universe at an accelerating rate, whose consequences will be felt on the scale of the entire cosmic future. The vacuum is not waiting to be dangerous. It is already consequential in ways we can measure. The danger and the activity are present tense, a complete accounting. 7 things that make empty space genuinely dangerous. The quantum vacuum seethes with virtual particle activity that manipulates atoms, creates forces between separated objects, triggers the spontaneous emission of photons from excited atoms, and has been measured in laboratory experiments to extraordinary precision. The nothing is doing something. The vacuum energy has a theoretical value that is 120 orders of magnitude larger than the observed cosmological constant, representing the most embarrassing discrepancy between theory and observation in physics history, while the tiny residual dark energy that survived whatever cancellation mechanism operates is sufficient to drive the accelerating expansion that will determine the ultimate fate of the universe. The Higgs field's non-zero vacuum expectation value gives particles their masses and makes atoms possible. But current calculations of the Higgs potential suggest the vacuum may be sitting in a local rather than global minimum, making the vacuum metastable and potentially subject to decay. Vacuum decay, if it occurs, would produce a bubble of true vacuum expanding at the speed of light, within which the laws of physics are different from ours in ways that preclude atoms and life. And this bubble could already have nucleated somewhere in the observable universe, without any possibility of advance warning reaching us before the bubble wall arrives. The Hawking radiation that black holes emit is a vacuum process, and the thermal character of that radiation is the source of the black hole information paradox, revealing a fundamental conflict between quantum mechanics and general relativity that remains unresolved. The Unruh effect shows that what counts as empty space and what counts as particle-filled space depends on the observer's state of motion. And the same mechanism produces particle creation from the vacuum by the expanding universe itself, representing the last physical process that will operate in the far future. The vacuum has already undergone multiple phase transitions in the universe's history, including the electroweak phase transition that gave particles their masses, and the inflationary transition that produced the initial conditions for cosmic structure, and may undergo further transitions in the future. 7 discoveries, each one revealing a different way in which the nothing is more consequential than anything. What does all of this mean? We began with the assumption that empty space is the absence of things, the background, the blank slate against which events occur, the nothing in which the something exists. Every discovery we have explored tonight challenges that assumption. Empty space is not the absence of things. It is the presence of something we are still struggling to understand, something whose properties determine the masses of particles, drive the expansion of the universe, create forces between separated objects, produce radiation from black holes, and may eventually restructure itself in ways that end physics as we know it. The vacuum is not the background against which the universe plays out. It is one of the universe's most active participants, perhaps the most consequential participant. The specific configuration of quantum fields that constitutes empty space, the specific value of the Higgs field, The specific amount of dark energy, the specific stability or metastability of the vacuum, determines what kind of universe is possible. Change the vacuum and you change everything. We exist in a specific vacuum, a vacuum that has the right properties for atoms to be stable, for chemistry to work, for stars to burn for billions of years, for planets to form and cool and develop the conditions for life. We did not choose this vacuum. We are the product of it, and we exist in an era when the vacuum's properties are, as far as we can determine, stable. The vacuum has not decayed in the 13.8 billion years of cosmic history that produced us. It has been consistent enough, reliable enough, to allow the extraordinarily improbable sequence of events that produced conscious beings capable of asking why empty space is dangerous. The vacuum gave us everything. The same vacuum that may eventually take it away. The empty space around you right now is not empty. It contains the energy that drives the universe's expansion. It contains the field that gives your atoms their masses. It contains the fluctuations that modify your atomic energy levels and trigger the emission of light. It contains the possibility, however remote, of a bubble of different physics expanding at the speed of light from some distant point. It is the most consequential nothing that has ever existed. And understanding what it is, understanding why it has the specific properties it has, why the cosmological constant is the value it is, rather than the value quantum field theory predicts, why the Higgs field has the vacuum expectation value it has rather than zero or some other value, why the vacuum is apparently stable or metastable rather than unstable, is the most important frontier in fundamental physics. The universe's most dangerous region is not a black hole singularity. It is not a neutron star surface. It is not a gamma ray burst. It is the space you are sitting in right now, the space between your atoms, the space between the Earth and the Moon, the space between the galaxies, empty space. The nothing that is doing everything. We have been studying the universe for the entire history of science. We have mapped its galaxies, measured its expansion, detected its gravitational waves, landed on its planets. And we have been doing all of this while sitting in a vacuum that we do not fully understand, that has properties we cannot explain, that may be fundamentally unstable, and that is, at every scale from the subatomic to the cosmological, doing things that we are only beginning to appreciate. The vacuum is not the absence of physics. It is the foundation of physics. And the foundation is stranger, richer, more active, and more dangerous than anyone who invented the word vacuum could have imagined when they used it to mean nothing. There is no nothing. There is only the vacuum. And the vacuum is everything. Shocking discovery. Number 6. The expanding vacuum is creating particles from nothing right now. There is a phenomenon called the Unruh effect, predicted by William Unruh in 1976. That reveals something extraordinary about the relationship between the quantum vacuum, acceleration, and the nature of particles themselves. An observer at rest in empty space sees the quantum vacuum in its ground state. No particles, just the seething, fluctuating vacuum. But an observer who is accelerating through that same empty space sees something different. The accelerating observer sees thermal radiation, a bath of real particles with a temperature proportional to the acceleration. The same region of space, the same physical vacuum appears as empty from one observer's perspective and as filled with thermal radiation from another observer's perspective, simply because of their different states of motion. This is profoundly disorienting. It means that particles are not absolute. What counts as a particle depends on who is asking. An observer in uniform motion and an accelerating observer disagree about whether the vacuum contains particles. The accelerating observer does not see more particles because there is actually something there that the inertial observer misses. They see particles because accelerated motion changes the relationship between the observer and the quantum vacuum in a way that manifests as particle creation. The Unruh effect has never been directly measured because the temperatures involved for laboratory achievable accelerations are extraordinarily small, far below what any current detector can distinguish from background noise. But the effect is theoretically well established and is mathematically closely related to Hawking radiation, which has been extensively studied and is more widely accepted. The Unruh effect reveals something about the nature of the vacuum that is deeply counterintuitive. There is no observer-independent answer to the question of how many particles are in a given region of space. The answer depends on the observer's state of motion. The vacuum that appears empty to one observer appears full to another. This has practical implications for cosmology. The universe itself is expanding, and the expansion has a horizon, the cosmic event horizon, beyond which events cannot communicate with us. This horizon is similar in important respects to the event horizon of a black hole. And just as black holes produce Hawking radiation from their event horizons, the cosmic event horizon produces a form of radiation called de Sitter radiation, or Gibbons-Hawking radiation. This radiation is extraordinarily faint, with a temperature of about 10 to the minus 30. Kelvin, far below any measurable threshold. But it is physically real. The expanding universe, with its accelerating expansion driven by dark energy, is creating particles from the vacuum through the same mechanism by which black holes create Hawking radiation. The universe is manufacturing particles from empty space right now, not at a rate that has any significant macroscopic effect in the current era, but over cosmic timescales, as the universe continues to expand and the de Sitter temperature represents the ultimate minimum temperature the universe approaches. This vacuum particle production is the last remaining physical process. In the far future, after all stars have died and all matter has decayed, the de Sitter radiation of the expanding vacuum will be the only physical process still operating. The vacuum creates. It does not just sit there passively. It responds to geometry, to acceleration, to expansion by producing particles from nothing. This particle production is the vacuum's most active behavior, and in the long run, it may be the universe's last word.